Hello, good morning, everyone. I hope everyone is here. Let's start. I'm just thinking today. This is a question for you guys. So, all of you tried installing Hadoop?
Yes.
Okay. So, how many of you have still problems? Hello?
We're getting a lot of background noise.
Okay, I am not sure. Yeah, somebody. Yeah, now it is down. Okay, all right.
Yeah.
So you're able to install Hadoop and then get to the browser and see the name node and job tracker web pages. Yes. Okay, good. So I'm assuming I'm treating that as an S. So let's go ahead and start practicing some commands on Hadoop file system. So Santosh, you're there?
Yes, sir. I'm here.
Okay, so I'm going to make you the presenter.
Okay, sir. Okay.
You can start going through the various different file system commands. Okay?
Sure.
Yeah.
Hi, good morning, everyone. Today, let's learn a few commands, file system commands of Hadoop, and these are the few commands here. Like yesterday, I showed you a command like to copy from our local file system. That's from our local file system into the Hadoop file system. So that's going to be our first command today. So I have a command that I have this file leo.txt in my local file system. Okay, I'm going to copy it to my DFS, okay, the Hadoop file system. The command for that is bin Hadoop, and before that I'll just show you like what are the files I have in my file system. See, this command is used to list all the files within the root, okay? And if you want to browse the files which are within input, then type in input here. So these are the files which you can see, okay? And the rewrite permissions, the username, group name, and the date, time, everything. And these are the files which are inside input, okay? So now I'm gonna copy the leo.txt file which is on my local file system to the input folder, okay? We'll use a command known as copy from local. That is copy and capital F and capital L. And in local it's located in my home directory, that's in documents directory. So I'm going to give the path home, Hadoop is the username, then documents and the file name leo.txt, and I'm copying it to the location input inside input, okay? Yes. Now let's display the files which are inside input, within input. See, now you can see the file leo.txt. So there is a command to copy from local, okay? Okay. And as you can see here, this is another command. Bin Hadoop fs make directory stocks. This creates a directory name stock within the file system. and you can check it by typing the command ls. Yes. Hi. FS is our local file system, whereas DFS is the Hadoop file system, distributed file system. Okay. Okay.
Both are same. Just Santosh, both are same. Just in the
Okay.
earlier versions, they were just using DFS. Now they have come up with FS. Okay.
Okay. Okay.
So both are same. Yeah. Sorry. Go ahead.
Okay. Okay. And here is the command that is copy to local. Now let's copy a. Sorry. Okay, now let's copy this the same layer.txt file into somewhere onto my desktop. Okay, as you can see, I mean there's no layer.txt file on my desktop. I'm copying now from my Hadoop file system to local file system. Okay, so to copy something from our Hadoop file system to the local file system, we use a command copy to local.
So how will it copy? Because earlier it was in the blocks of 64 MB, and now TXT will be having block size different. So
Hello.
yeah, how that is taken care?
I mean
That is
the block
transparent
size
to
you're
user.
asking.
Yes.
See, that
Yes,
is very transparent to the user. So I'll answer that question, Santosh. It's very transparent
Okay.
to the user. So the file size is less means that in this case there will be just one block. It need not be 64 MB. If the file size is bigger than 64 MB, then it will split into blocks. Otherwise, there will be only one block. And in this case, when you copy a file into Hadoop file system, we don't see what in the command line. You don't see what is happening, but internally, as you know, the file is split into pieces, and those pieces are copied to data nodes. Okay, so each piece is about 64 MB, which is determined by the HDFS block size. And if you really want to see, you should copy about a 1 GB file, and then you should go to data nodes, and you should see that there are blocks inside the data node directory. Okay, does that answer your question?
Hello.
Yeah, does that answer the question?
Yes, thank you. I got it.
Okay. Yes. Yeah. Let's copy from local. We have the other command which we used earlier.
Yeah, Santosh, repeat that command also.
Yeah, sure, sir. I'll do that. I mean, earlier we did use a command known as copy from local. Okay, so what this does is it copies this layer.txt file into our input folder. Okay, so when we did execute this command, it copied over here. If you want, I'll try it out in a different location. Okay, user, we have another folder that's user. In here I'm copying the file, that leo.txt, that's a temporary file. Okay, now I'm gonna display the list. And in here you can see the leo.txt file where we are copying the file from a local file system to the DFS file system. Okay, Hadoop file system. And the other command which we used was this to copy a file which is in our Hadoop file system into our local file system. Okay, here we use a command like which is in input, the leo.txt file which is in the input folder. Now it's on our desktop, which we can see here. Okay, so okay, yeah, as I told you, we did create a directory that's called stocks. Okay, and we can check that by using this command. See, it's a directory which has been, to create a directory we use this command. Okay, that is bin hadoop fs -make directory, that's mkdir, and the stocks, and to display that, here is a command. Okay, and now let's go ahead and remove the directory that which we created earlier, that's nothing but stocks, and this is the command to remove that. Yes, so now let's go ahead and list it. See, now you can't see the directory which we created earlier, that is stocks. Can we? All right. So let's go ahead and delete a file that which we created, that's leo.txt. Okay, I mean earlier we are having a leo.txt under the user directory, so let's delete it now, remove it. So you can see the message deleted HDFS. Now let's list it. This is the 4 files which are within the user, and we don't see leo.txt. Can we? So in this way we can remove a directory and a file from the Hadoop file system. And this is a command to clear the trash. It's Hadoop dfs-expunge. And the get command works similar to copy to local. Okay, this is the same thing. I mean, we are copying a file from the Hadoop file system onto our local file system. Gets files to the local file system. Okay. So let's see this test0 file, which is here. Okay, and under user test0, can you see this file? Let's try to copy onto our desktop now by using the command get. See, Hadoop dfs get zero. Let's copy into our desktop. Okay, see, let's now go ahead and check our desktop. You can see the file test0. This is similar to copy to local, the command. Okay, and Hadoop dfs copy source destination. It just copies a file from source to destination. Let's give source as sorry. And the destination is input folder. Okay, now let's go ahead and check the input. Yes, here we can see the test 0. It just copied the file from which is in user to the input folder. So, and we have another command which is like to check the disk user space, like how much disk space we have used, and the command for that is this one. I mean dus. Let's give the file name input a folder. So you can see this is the amount of space which is used by the input folder. And this will list all the files within the directory and specifies like how much amount of space that particular file has taken. Just -du, that's it, and it lists all the files. See, you can see the files which are within input, and this is the size of each file. And it's nothing but the recursive way of listing all the files within root. Okay. These are all the files you can see. And this CP, this one we use in an cluster mode. This is nothing but distribution copy. I mean distributed copy, which we use in a cluster environment. I mean this command we'll be using in future, and we'll go in further details with that later on. Okay, let's keep that for now. And see, these to move files from directory 1 to directory, and this is a command. Let's move a file. Okay. Like we are moving the files which are in user into the directory that is input. Okay. Now let's check and see the list of the user. See. Let's check the input. Here we can see the user directory. Now it's in input. We don't have the directory user anymore. It moved to input. And there's nothing but copy from local to SDFS. This acts as the same the command which we used initially. That's copy local copy from local. That's nothing but we are copying a file from our local file system to the Hadoop file system. Okay, let's go ahead and copy. Just okay. Let's copy the same layer.txt onto the root directory. Okay, we are copying the file that is layer.txt, which is on our desktop, to the root directory of the HDFS file system. Okay, now let's list the files. The root. Yes, now you can see the layer.txt file here. Just in this how we remove a file. I just showed you earlier. Just let's go ahead and remove the layer.txt file again. Yes, now it's deleted. See, now you can't find the file. That's how we remove a file from the Hadoop file system. And this way to set the replication factor, as we seen this replication factor yesterday, and this is how we set a replication factor. This is a command which we use to set a replication factor for this particular directory. Okay, that's a replication factor is to 3. Okay, and this is the status of a particular directory. This gives the status, the stat command, which gives the status of a particular directory. See, you can see the time and the date. Okay, and the next command is to test the file. So you can see in Hadoop TFS-test we have 3 options here, that is E, C, and Z and D. E is nothing but it checks to see if the file exists or not. Initially let's use the option -E, and the path URI is nothing but uniform resource index, which we are going to give the path of the file in the Hadoop file system. It returns 0. Yes, if it says that the file exists, the input file exists. Now let's go ahead and try something, some unknown file name, X YZ, and let's check what it returns. 1, because the file XYZ doesn't exist. I mean the directory of the file. Okay, and the next option in that is, let's use the Z command, option Z, check to see if the file is 0 length, return 0 if true. Yes. And the last option we have here is -t, check return 0 if the path is directory, else return 1. Let's try some. See, file doesn't exist. See, it gives 255. That's nothing but -1. So this is how you can test a file using the below commands and the options, those 3 options. And that's it. This to create an empty file. I created an empty file that's XYZ. We can list that. See. There's nothing in the file. That's why it didn't display anything. Okay, it's just an empty file. And this is the command that's output the fill in the text format. You can see it. List the files. Let's check where is leo.txt now. See, leo.txt is present in the input folder, and let's display the text. So this is the content which is in the leo.txt. It's a file which has this content. Okay, it's just the content, and it displays on the console directly, whatever, no matter what the content is in the particular file. As Sir was telling us like yesterday, please do not display any content which is which has huge amount of massive data in it, like 1 TB of data. In case if you by mistake if you type that command, it takes hours for it to display itself, and you may face with problems too. So it's better to avoid that. And this displays the tail of that particular file in last few lines, like current 15 lines. You can see. Let's display not the complete content in that particular file, that's leo.txt. Let's just display the last few lines. You can see it here. See, earlier we had that complete data. Now you can see these are the lines. That's how we use the command tail in order to display. In case if you have a massive, a huge number, like 50 lines of code or anything, so we just want to see the last 10 lines of it, then please to use this command, the tail command. And this is to add a new task tracker. This is a command. And then let's go ahead. Okay, this is the cluster balancing, which will be looking in future. And then these are the change mode options, like changing the username and the group name of the particular files. I mean, if you have a different user, okay, type in I have a single user over here.
Hello. Yes.
Yes. Hello. Okay, I have a single user here, that is Hadoop. Hadoop. Okay, in case if you have a different user, in case Jack, let me take, if I have another user, Jack, and if he wants to take the ownership of these files, I can just type in the command here, Hadoop TFS chown, and instead of in the username, I'll type in Jack and the group name and the file names. So those files will be owned by Jack, no matter who the user is. So you can just switch the ownership, and these are the switch the mode of that particular files. So these are the two commands which we use, and that's it. And this is a command to show us the archives. See, this shows the complete list. Hello, sir. Hello. Hello. Can you hear me?
Yeah. Okay, guys.
Yes, we're listening.
Yes.
Yeah. Let me.
Yes.
Any questions?
No.
So there are no questions. What we will do is, I have a couple of slides to share with. So we'll just go with MapReduce. We'll discuss one more time the MapReduce, and then next class we'll run some examples of MapReduce. Okay. So all of you see my screen?
Yes.
Okay. So as we decided, right? We have been looking at the Hadoop file system. So the Hadoop file system is helping us to store, large number of files with a huge size. So we're not looking at small sized files. We're looking at huge number of files, right? And at the same time, large size. So it is more efficient to store large files in Hadoop file system compared to small files, because the overhead of transfer of small files is huge. In order to avoid that, it is recommended to store huge number of large files, especially any files related to logging, right? Any files related to
40 minutes
transactions.
Okay.
Yeah. So those are the things that are getting stored in Hadoop file system. So some of the examples of a large data set processing. So once these files are stored, what is the use of these files? So end of the day, we have to find out what is in it and how do you process those files. For example, if you want to see Google logs and how many people have searched for Obama, let's say, for example, in the past 1 month, right? They have huge number of logs that is stored in their web servers. So they have to open those logs and then go through every line and see how many people have searched for Obama. Or they want to find out which part of the world is generating more search traffic, or what is the most popular topic that people are searching. So these are the things that you should see for analyzing. So today what they're doing is they're storing all the Twitter messages in Hadoop as one big file, and then they're analyzing all those Twitter messages for trends. So what is that people are discussing? Are they discussing about politics or movies or any particular video? What is the trend? Is there a negative sense or a positive sense? All kinds of things people are doing. All this is possible because of two things. One, we can process huge amount of data using a huge distributed cluster. And second is that we are trying to process the unstructured data. So there is no structure compared to relational database systems where you have data organized in tables. Data is systematically organized in tables in RDBMS, whereas here we don't have any structure. So only the map and the reduce parts of the function should understand the structure. Otherwise, anything that you want to store, you can store in Hadoop file system without worrying about what would happen if you store it. You only worry about it when you are processing it. Until that point of time, Hadoop file system will act as a sink. You can push anything into Hadoop file system. Whether you want it or not, people are trying to push as much as data as possible into Hadoop file system and then worry about it later. Financial companies in US, in order to follow regulations, they have to keep the data, transactions data, log data for more than 3 years. So they're trying to push everything to Hadoop file system. It's a very inexpensive way to store large files and maintain them without worrying about losing, because Hadoop file system provides the capability of replication, which can help keep these files intact for a long period to come. Okay, that is the small introduction. Now we are trying to process this data, right? So we process structured, unstructured, semi-structured data. Structure means we know that it is in terms of the format of the data, it's fixed. For example, relational database system, the format of the data is fixed. Semi-structured means it has some structure, but it's not complete. Unstructured means it's just raw text. For example, if you go search a web page and the output of the content of the web page is very unstructured. It's not easy to find a structure out of that. So those are the things that examples of structured, semi-structured, and unstructured data. So we need when we are trying to analyze this kind of data, which sometimes has structure and which sometimes doesn't have structure, we need a model. We need a programming model that should basically help us not worry about the structure at all, right? And you should not. So the user should not worry about the intricacies of how my program is going to work. A user should not worry about whether my program is going to run and what block it is going to run, which part of the file it is going to run. So the programming model has to be simple, where if you put this code to analyze a particular file, it should apply to the whole file. So the user should not worry about distributing the program to the machines where the computation is happening. So we'll see that in a minute. So this is another paradigm that we discussed earlier. In distributed systems, we move the program to the place where data is. So we don't move the data. So in this model, what we do is, when you write a small program to analyze the data, we move this program to the computation cluster. So that is where the data is. So the program runs on that data and the results are aggregated and then you get the results. Okay. So that is how the programming model has been designed. Okay, in a very layman terms. As an administrator, you will not do much of programming, but it is good to know, right? What are the aims and goals behind the programming model? So the model should basically spread the work to more than one machine, right? And then the problems are mostly, so what are the challenges in that? We have seen that it's going to be communication and coordination, recovering from machine failures, status and progress reporting, debugging, and optimization, right? And locality. So these are some of the challenges when you want to distribute a program to remote machines and run those programs. For example, the remote machine may not respond. The program may, the network may be a failure. And if the remote machine is actually working on a task, how do you report the status of the task back to the central master? Is there any optimization we can do, right? In the sense that, okay, we push the program to the place where data is. What if data is not there? Data is in some other machine. So these are some of the problems or challenges that the MapReduce address, and then it addresses very elegantly. So MapReduce, as a programmer or as a developer, we do not have to worry about these issues because MapReduce helps us to solve these problems transparently. We don't even know that how these problems are solved, but for a developer, he doesn't have to know, right? So that is how the work has, or the programming model, or that is how the MapReduce works. So typically, when you are looking for, when someone asks you as an administrator, suggest me a configuration for a map for a Hadoop cluster. Suggest me a machine configuration for a machine cluster, for a Hadoop cluster. Then you can say it depends on the kind of job that you want to run. Depends on what kind of files you want to store. Depends upon the workloads. Do you have diverse workloads? Diverse in the sense, is it memory intensive? Is it memory iterative? Hello? 1 second, please. Road number 9, right side, Lakshmi Medical Shop Pakkana, Sandulo. Lakshmi Medical Shop Pakkana, Sandulo. Second, first water tank munde right side. Right side. 5 నిమిషాలు పడుతుంది. Right, వచ్చేసి. Sorry guys. So generally the configuration for the compute machines it depends on the applications, but generally it should have a quad core. There should be a quad core machines. And minimum 4 gigs to 16 gigs of RAM, especially when you are running lots of jobs which are memory intensive, then you need 16 gigs of RAM. Otherwise, about 8 gigs is sufficient. So the machines, even though we say unreliable machines, the machines have to be decently good. We cannot definitely put desktops from Dell or HP. You can still put them, but you may not get the returns out of it. So you can still, for your lab purpose, you can make a cluster out of desktops. No problem, it will still work. They are still reliable, but generally they need to go for good rack servers or blade servers, which are compact in nature. So in one rack, you can have a 64 node cluster. So that's the kind of thing that people are looking for. Today, if you see Yahoo, they had 5 years ago or 6 years ago, 2 floors of their office is completely data center. Now they have only half the floor because they moved on from huge tower servers to blade servers, and with the same capacity, same computing power, they were able to save on real estate space. So better to go for compact servers which are more powerful. Any questions here? And then about the hard disks. Generally, data nodes require a huge amount of hard disks. So a 2 terabyte disks, have 2 separate disks would be good, so that it can balance upon on several disks. So if you have only one disk, and if this data node is accessed very frequently, then the speed, then the lot of IO is happening on the disk. So instead, if you have two disks, it can schedule the read between two different disks, which can increase the throughput, the disk read throughput. Okay, so that's how you design the cluster. So we will, when we actually discuss the topology, the network topology of a cluster in one of the classes, I will give you the structure of the network and how you organize the machines in the Hadoop cluster. So let's in this class, so that this is a prelude to what is going to come next. We are going to understand what is MapReduce. I know we took the post office example and run through it and understand how the letters are sorted, across zip codes. So now we're going to go a little bit deeper and try to understand how MapReduce is going to function. So let's say this is how the MapReduce is. Let's say you have a lot of pictures with different shapes here, right? And what you want to do is you want to make sure you want to group all the pictures with common shape into one group. That is the goal, right? That is the goal. So traditionally what you do is, if you were asked to do this, you take a particular shape and then you put it into one place and then take another shape and see if it matches the shape. If it matches, you put it into the same place, otherwise you put it in a different place. So this you can do provided the data is small, provided the data is maybe 100 shapes. What if you have 1,000,000 shapes? How do you do it, right? Then you need a computer or you need a distributed computer. So what you do is you divide the task into pieces. So that's what it is done in this picture. You take this huge amount of shapes and then divide it into pieces. So you can see it is not shown here. In the subsequent pictures I'll show you that. So what you will see is the data is divided into pieces, and each piece is being searched for the shape, and whatever is the output, you can see the map output. You can see the hexagon. Hexagon is having a count of 1, triangle blue color is 1, orange color triangle is 2, so on and so forth. So each map task produces some output, not all, right? Because this input is huge, we are trying to split the data and then process the data separately into pieces. So generally each map processes one block of data at a time, but it need not be so. You can split the input into different sizes. Okay, so each split, number of split is equal to the number of maps. Okay, so number of splits is equal to the number of maps. Now the output of map is nothing but each shape and its count, right? So now I have output from different machines with each of these shapes and different counts. Now what I want to do is I want to merge all this. When I want to merge all this, I want to find out if all these hexagons coming from two different places, can I add them together? So in the first map task I have 1, in the second map task I have 2. When I add them, I have 3. Similarly, you can see for other shapes the count has been added. This is a simple illustration of a MapReduce. 1 second please. Hello? Sorry guys. So this is another way of representing the same thing. Okay, so you see a map, shuffle and reduce. So you take the input slip on the left hand side, you see 3 blocks of data, right? Each of this represent part of your input. So for you it is for processing, it is a part of the input. But if you look at the Hadoop file system, right, it could be a directory, it could be one file split into pieces, it could be series of directories, it could be hundreds of files split in some fashion. All of them are organized as splits and they are submitted as input to the map function. So the output of map function, it is doing something so that it reduces the amount of data into intermediate output. So the output of map is called as intermediate output. Then the intermediate output, all the common intermediate outputs are shuffled and sent to one reduce function. For example, in this case, if you see all the data with red color is sent to one reduce function. Similarly, all the data with yellow is sent to another reduce function, and the one with the blue is sent to another reduce function. So what we're trying to say here is that common function, common data that has similar properties is sent to one reduce function. So what the reduce function does is, it takes this input and processes further and then gives you the output. So let's illustrate one more time. So we have huge amount of data on the left hand side. We split into pieces, process through the map. The output of the map is shuffled to all the reduce functions. So in the reduce function, we will do some more processing, and then output is stored into a disk again. So the huge amount of data on the left hand side is stored into a very small amount of data on the right hand side. So for example, if you're looking for number of searches per day in Google, you will see so many log files on the left hand side, but the output is just a count, an integer, right? So the amount of data, so a lot of this kind of computations can be done on the data. So generally the input is huge and the output is in a much lesser size compared to the input. That is the whole reason. That's why they call this map and reduce, because it is reduced because you're trying to reduce the size of the input into output, which is much less compared to the size of the input. So this shuffling happens because I think we remember in the post office example, when you sort the letters, the zip code for a particular country can be in any of the map tasks. So I need to group all the zip codes to a common bin or a common sink. So that means the output of map task has to be sent to each of these reducers. Okay, so there is a lot of I/O happening here. You should see that the output of the map is stored in a local disk. From that disk, framework will take that file and copy to reduce. So a lot of I/O, a lot of network is being utilized in this space. So that is also a challenge, but it happens transparently. But as an administrator, you would be worried about this aspect, where people can complain that if somebody is doing a map reduce operation heavily, then you should see that the network, other users may complain that look, my map reduce task is not happening. So we will see later that we will be scheduling these jobs such a way that people will be able to utilize the cluster productively without worrying about whether their job can run or not. So let's take a word count example. Let's say if you want to find out of 20 billion documents that are there in the web, you want to find out how many words occur and what count, right? So obviously such a 20 billion documents I cannot process in one machine, so I had to split it. So split the data. So in this case the input is 3 lines, okay, just to illustrate the point, but generally the input is very large. So you split the data into pieces, and then each split is sent to a map task, and the map task will just split the line into pieces and count the words. So in this particular example, if you take the first split, deer, bee, river, so the deer is 1, bear is 1, river is 1. So the output of a map is nothing but the count of the words, how many times the word has occurred in that split. So then it is shuffled. Similarly, the other map tasks are done. Once all the map tasks are complete, the shuffling happens. So all the words with bear will be sorted together as 1. So if you look at it, all the words with bear, car and deer and river are merged together and they are sent to the reduce function. So if you see that the bear, car, deer and river, all of them have a common key, bear, and in the reduce function what we are saying, we are taking the bear and then summing all the counts. So in this case the final result says that the bear occurs twice, car occurs thrice, and so on and so forth. So basically what we took is, we took the input and then we processed it and counted the word count that occurs in all these documents. Generally this is done over several hundreds and thousands of documents. Any question here? So I'll just go one more example. Let's say I have another example. I have this input of different files. I go through a process called a map, and then I pick up every line, and then I count the word, and then I group those words which are similar in nature, and then I pass it to the reduce function. So what the reduce does is it will count all the common words and then add the output. So if a word occurs in multiple pages, like 2-3 times, those counts are added. So this is another illustration of the same thing. You have if you try to compare it to our distributed cluster, you would see that there are multiple nodes: node 1, node 2, node 3, like that, node 5, node 1000, node 2000, like that. So you have the data as the input, the mapping process happens, and there is a output that is saved, intermediate output saved. Same thing happens on every node. Again, each node will take one split. Each node will take one split and process the data. So the output of node 1 is sent to the reducing process, and then the output of node 1 is, you can see, is sent to all the reduce tasks. Similarly, output of node 2 is sent to all the tasks, and same as node 3. In the node you will see that reduce operation is happening. Okay, so now this is the last slide for today. This is very important. So we are trying to come up with a programming model slightly differently. So we have a data store which is an input. So the input is a key value pair. The input is a key value pair, and we are sending it to a map, and then the map emits key and values. The map emits key and values, and then all the outputs with a common key are grouped in the shuffle, which is called as a barrier, aggregates intermediate values by output key. So the output key is key 1, key 2, key 3. All the values with the common key is aggregated, and all the values with a common key is sent to one reduce function. Right? That is what is happening. So any questions so far? Hello? Any questions so far?
No.
No.
Okay, so this is, I think if you understand this process, it's pretty much, it becomes easy to explain the rest of the topics later. Okay, so today's class, that is it for today's class. So we'll continue on MapReduce, and tomorrow I think we will execute some sample MapReduce programs on your Hadoop cluster that you have just built. So Santosh will show some examples of how to run MapReduce tasks on the cluster. So you should be able to use those commands as it is and run those examples. Okay. All right.
Okay.
Thank you for.
And one more thing, we don't get the documents. Like we did not get the installation guide.
We are still trying to get to you. So I will post those documents today. Again, please do not share this document with others. We have put these documents together with a lot of hard work. Okay. And yeah, we will send these documents.
And even we want the document for today's also, like we discussed commands, right?
Yes. So we will send those two. We will send it to Kathy, and then they will be forwarding the documents to you. Okay.
Okay. Thank you.
We will do it. Thanks. See you guys tomorrow. Bye.
Bye. Have a nice day.